you had the time for a coffee or tea or breakfast or dinner, wherever you are in the world. And so we have heard already quite a bit about transient localization or delocalization. And now we'll hear about Simone Fratini about the method, transient, or the theory of transient localization applied to organic semiconductors and beyond. Simone, please.
Okay, thank you. Let me just put my counter. Yes. So I'll give a brief summary review about all this transient localization stuff. So there is some like initial insight and results, and then I'll try to talk about newer topics that we are trying to analyze. Well, here there is a list of collaborators. I hope you can see my pointer from the theory side and from experiments. Lately, we have been working a lot with Henning. Actually, he has given the perfect theory talk. So I will mostly skip all what I wanted to say and just go to the conclusions. Where did we start from? Basically, the problem, as also Antoine has correctly said before me, is this number here. So these materials, organic semiconductors, they live in some space which is a no man's land in between well-known theories. And the main problem here was to understand how the mobility can be so low and yet exhibit a band-like temperature dependence, which means that mobility goes down with temperature. So this is very similar to what Antoine has shown. Up here, this is an arrow with values of mobility. Organic crystals are here in between. On the right, you have the good semiconductors where you can apply band theory, and on the left, the disordered ones or strongly interacting ones where the mechanism of transport is hopping. And what really makes the difference between these two is the fact that is the mean free path. So to apply band theory, you need mean free paths that are larger than the lattice spacing, because you start from a wave description of the carriers, and you can't define waves if the mean free path is shorter than the lattice spacing. And so typically setting the mean free path to one lattice spacing gives you mobilities that are right at the values that you encounter in organic crystals. So I'll take a really hardcore theoretical physicist perspective here, and just go to the basics. And the basics, well, for historical reasons, is what is written here, which is the simplest model that has all the ingredients in it. And this is the Holstein model. So of course, the physics and chemistry is much more complicated in these systems, but the basic phenomenon is already contained in this model. And it's quite surprising that this model has been around for 70 years or 60 years. And nobody had realized that there was an unexplored regime. And it's actually thanks to these organic semiconductors that we hit right where that regime was. So the model is written here. There is this first term here. There's a tight binding description of transfer from molecule to molecule. And the second term is an interaction. What we call interaction as physicists is different from what chemists call interaction. But here is really a coupling between the charge density and some deformation. And this deformation has dynamics, and the dynamics is described by this phonon Hamiltonian. All conclusions drawn from here, or almost all of them, work also for other types of interactions, like the Peierls type or non-local interactions that apply to organic semiconductors. So the interesting thing here is to show a phase diagram as a function of two parameters. One is temperature, and this is the parameter that was really neglected at the beginning. And the other one is this dimensionless coupling lambda, that is essentially the ratio between the energy you require to form a polaron, or you gain in forming a polaron, and the bandwidth. So if you're at low temperatures, this is all well known. At weak coupling, you are in a free or almost free electron regime, and you can apply band theory. And then when you increase the coupling, you hit some critical value where you form polarons. So these are also, they can also move as extended like waves, but with much larger effective masses. When you increase the temperature, when you're in this polaronic regime, you know that you will go from a tunneling regime in transport to activated hopping. And this is where Marcus theory works. But so all this part here on the left was left unexplored. And basically because there were no materials that were falling in this area. So what happens here is that if you try to draw a line that marks where the mean free path equals the lattice spacing, you get this red dotted line here that scales like 1 over lambda. So actually the regime where you can apply band theory is down here, and then nobody really knew what to do up here. So what happens is that even though the coupling of holes to vibrations is weak or moderate, there is such a high population of vibrational states, of thermal population, that this thing can be seen as a very strongly fluctuating environment. And you can actually calculate analytically the energy spread of these fluctuations in terms of the parameters of the model. And you see that this thing can be very large, even though lambda is small, if temperature is large enough. So you can have fluctuations that are of the order of the bandwidth. So what is happening here is that if you take a snapshot of your material at some instant in time, the carrier will see a very disordered environment. So if this environment was just frozen, then we know how to solve a Hamiltonian with static disorder, and we know that the wave functions will localize at the minima of this potential. Now, localized means that nothing is moving, and so the mobility would be strictly equal to 0. However, it's not true that nothing is moving, because this random potential is fluctuating with a typical scale, and this scale is the vibrational scale that I called here omega naught. And this is what allows everything to move, or as Henning was saying, to surf on these molecular fluctuations. So these are, I'll show you this slide with 3 basic properties that come out of this regime. So first thing is this mean square displacement, or here what I've drawn is the square root of the mean square displacement. So this is a typical semi-classical behavior that you encounter in good clean silicon. The spread of a wave function when you throw it into material, it has a first regime that is ballistic, where just the spread goes linear with time. And then you hit this typical scattering time, and then in this log scale you change slope, which means that you really enter a diffusive regime where the spread goes like square root of time. Now, the opposite limit is where you have full localization. So in presence of static disorder, you also start ballistic, but then there is some time where just the wave function stops moving because it localizes in this minima that I was showing before. So what is this transient localization? Well, it's something in between. It's shown here at short times. And by short, I mean shorter than the typical time scale of molecular vibrations. The carriers don't know that the disorder is moving because these motions haven't been activated yet. So it will follow, the carriers will follow the localization curve. But then as soon as they realize that the disorder potential is shaking, they will start diffusing. Now, the consequence is that the diffusion constant and hence the mobility will be lower than the semi-classical one typically because of this time lag before it can start diffusing. And this is what allows the breakdown of this Motyov-Feregal condition, or having apparent mean free paths, just apparent mean free paths that are shorter than the lattice spacing. Now, the second consequence is that the mobility, I'll come back to this formula later, but just take it now here. There is this prefactor that comes from Einstein's relation. And so you already have a factor of temperature here. And also the localization length here depends on temperature because the amount of disorder depends on the temperature. So you end up having a mobility that scales like a power law. So you have a power law, yet is not band-like. And the third property, so this was, we were analyzing already at the beginning 10 years ago. There is this exact relationship that holds in semiconductors that relates this mean square displacement to the optical absorption. And I repeat, this for independent electrons or holes, this is exact. So if you just Fourier transform these curves here and apply this detailed balance prefactor here, you can actually predict how the material absorbs light. Well, not the material, but the extra carriers that you have added and that are moving. And so I'm using the same symbols here. So the dashed here is for semi-classical transfer, band transfer, you get a Drude peak. This is well known in semiconductors and in metals. In the other two cases, which is transient localization and localization, this Drude peak has shifted to a finite frequency peak. Well, you have depleted actually this region of low frequencies simply because you have suppressed the DC conductivity or the mobility. And this will be important in the last part of my talk. So there is some maybe ambiguity in what is transient localization theory. What I mean here by transient localization theory is just a specific flavor where we solve the simple problem with static molecular displacements, and then we apply this relaxation time approximation to mimic the dynamics. So basically, if you want to analyze a material like this, you need to evaluate by some ab initio method the fluctuations of the transfer integrals and the fluctuations of the site energies. Then you solve your problem for frozen displacements, like frozen molecules. And this you can do by a variety of methods. Then you apply this relaxation time approximation. And this, with this, you can calculate your observables, mobility, optical conductivity. We are working on, or we plan to work on Seebeck effect. So there is an open access code, but you can actually rebuild a code. It's very simple. Everything is written here. So what have we learned in 10 years now? Okay, this theory is not the best theory, is not as accurate as other theories. It's actually semi-quantitatively accurate right in the regime that we're interested in. So we are lucky in that. And it's fast. So it's very useful for screening of materials. Yeah, as I was saying, there's a bunch of more accurate theories. Unfortunately, some of them can't really be applied beyond like an idealized chain with few sites. So for real applications, they are not very good. But of course, comparison of these theories to benchmark simpler approaches is always welcome. Now, the other characteristic is that all the relevant information is condensed into one analytical formula. So why is this important? Well, because now if you want to improve your material, you know where to act. And actually you can act on, well, temperature you can vary, because if you want a material to work at room temperature, this is what you have. So you basically can change this localization length and this time scale. And on deeper grounds, well, first of all, this is nice because we had this sketch of how things would move, and then by seeing the movies, like the movie that was shown in the previous talk, it really looks like what we had imagined, and we were kind of that was a wild guess somehow, just by reading this formula, and it seems to work. So that's nice. But on deeper grounds, there is something here that is really a change of paradigm, because we are used to think of the relevant parameters being either effective mass and mean free path or activation energy. And here in this regime, it's really this localization length and this inelastic time that are governing transport. So this is very useful because it's really straightforward to at least try to give guidelines for improvement of performances. So we want to act on this, basically on this length squared. So we have two knobs. One is band structure, and the other one is the amount of thermal disorder. So this is work we have done a few years ago with Alessandro Torrisi. We realized that to a good approximation, you can map almost every organic semiconductor into this simple structure with three principal transfer integrals. Sorry. So this JA, JB, and JC. And then evaluate the localization length as a function of the band structure. And here the color code is more localized is black, and more delocalized or more conducting is white. So you see that, for example, if you are one-dimensional, which means one of these axes is all black, so performances are very poor. And if you are here on the white spot, this is the best spot. So this corresponds to an isotropic material with all equal values of the transfer integrals. Now you can put materials on here, and they all pretty much fall either on top of this meridian here or very close to it. So you can actually characterize all band structures by an angle theta that is the angle with respect to this vertical axis here. So the second knob is the amount of disorder. So here I'm showing the mobility, how it varies when you increase your amount of disorder. And in all cases, 1D isotropic, I've taken the band structure of green. this goes down very fast with disorder. So you have a degradation that goes faster than disorder squared. So the take-home message is that you should try to look for isotropic band structures, minimize molecular disorder, and you have a lot of margin for improvement. And as Henning was correctly saying, it's not really the absolute value of the transfer integrals that matter, because you might have very large transfer integrals in one direction, but then the thing is one-dimensional and it's very, very sensitive to disorder, and you'll get localization and very low mobilities. So these two informations here, the two knobs can be condensed together in one graph. That is here. So here I have this band structure parameter theta that controls how isotropic it is. So 1D would be here, isotropic would be here, and on the left axis it's disorder. So first thing, of course, if disorder is low, you have band transport. If disorder is high, you have transient localization. Second thing, for a given disorder, this is what you're seeing here. It's easier to get band transport if you're on an isotropic material than on a 1D. So this is just a summary of what was written there. And now we can put all these materials on this phase diagram. And so there is some bad luck because they're all on the wrong side. Well, it's good luck for theory because they're on the right side for transient localization theory, but for performances, they're all on the wrong side, and you never hit this band transport regime. And so the funny thing, or just puzzling thing, is that you have materials that have good band structures but bad disorder, materials with good disorder but bad band structures. And if you could just combine the good disorder and the good band structure, you could probably hit mobilities on the order of 50 centimeters squared per volt second or even higher. So how can you do that? Oops. So this is also what Henning was telling about. We've been working on trying to understand who is guilty of this disorder here. And here I'm putting an example for this functionalized DNTT. On the top panel here, you have just the amplitude of the fluctuations of the individual modes. So this is some mode resolved study. And you see that basically the amplitude of the modes is going down with frequency. This is what is expected for harmonic oscillators. There's not much room for improvement here. What is more interesting is how these modes couple to the carriers. And the interesting thing is that the amount of disorder that is carried by each mode is the product of these two numbers. So what's happening here is that this mode at very low frequency combines very large amplitude fluctuations and a very large coupling, and it actually takes 70% of the whole disorder just by itself. So this is what we call the killer mode. This is a sliding mode, not surprisingly. And one strategy to improve materials is just to try to disarm this mode. For example, by engineering the crystal structure so that the coupling, which is the derivative, the variation of the transfer integral with respect to distance at the equilibrium position, is minimized. So this seems to happen almost for the NTT, which has a bad band structure for other reasons, but this is a way to go. So just in the minute or so that I have left, we have been working recently on going beyond organic semiconductors with the same ideas, and in particular in metals and doped polymers. So again, I'll use my favorite Holstein model, and I'll track just the transient localization by the existence of this displaced through the peak that I was telling you about a few slides back. So this you have already seen. This is the sketch for semiconductors. This is where we started from. Now we did calculations for metals, and this is the phase diagram we find. These are real numbers. I mean, this is our real calculations, not a sketch. And you see that the phase diagram is essentially the same. So this transient localization is not limited to organic semiconductors. It should be seen in metals also. Now, has this been seen? The answer is here. If we associate this displaced through the peak with transient localization, then there is a lot of them everywhere. This is a list of materials. They are mostly strongly correlated metals, superconducting cuprates, organic conductors, Kagome metals. In all these, you see peaks that move with temperature. This indicates that thermal vibrations or some thermal fluctuations of whatever boson you have are playing a dominant role. And so maybe this thing that started with organic systems, it goes beyond that. And this is just what Henning was telling about in doped polymers, in this ion exchange polymers. It seems, well, we have done calculations with the same theory, including all like a description as accurate as possible of the disorder that is characteristic of these materials, and including also ion hole and hole hole interactions that become important at large electron concentrations. And if you calculate the conductivity, you basically get numbers that are in quantitative agreement with what is measured. So this is where we are going now. And because I'm already 2 minutes late, I will answer your questions, and thank you for your attention.
Thank you very much, Simone, for giving us a flavor of what transient localization theory actually means. So we have a couple of questions. There is one question which I think relates to the possibility of calculating the full spectrum of the relaxation times that enter into the transient delocalization model. So is it possible to actually get access to the full spectrum? You're using a single relaxation time. So, I mean, so what is the physical motivation for doing this? Is it possible to get access to the full spectrum?
Okay. Access to the full spectrum means, so this would be the input. This could be obtained by just calculating the spectrum of fluctuation. Now, how to include this in transient localization theory? This can be done. We haven't done it. Basically, what you have to do here in this basic equation for the relaxation, instead of just one relaxation, you should integrate over all times. So this can be done. It will give very similar results, and probably you can define an average relaxation time that does the job. But this is a good open question.
So is there something like an additive rule, like the Matheson rule for scattering in solids that you could apply there?
Well, actually, if you see the structure of the equations, this would be a convolution of all the possible taus, which means that it's probably a product in Laplace transform space. So it shouldn't be complicated, but this remains a very qualitative or phenomenological theory. So maybe you wouldn't gain much in precision. So it's better to improve other methods like surface hopping to go really realistic.
There's a second question that from Oleg that I also add, which is what is actually the role of intramolecular polaronic effect on transient localization? Because this is something that is ignored in the theory, right?
No, well, we have included it in some versions and in some papers because, provided that the frequency scales are really separate, then the only thing that happens, or to the first approximation, is to renormalize all the transfer integrals by just some rescaling.
Right. Yeah.
But because also the disorder fluctuations, like the fluctuations of transfer integrals will be scaled down, the ratio won't change. So to a first approximation, the effect is 0. And then, of course, we can discuss about higher orders, and then maybe it has some effect, but it's definitely not the dominant one.
Yeah. A question from Vitaly about the green-white sphere that is indeed beautiful, but based on that sphere, rubrine should be one of the worst interiors. Is it correct?
Well, but it has a very good, very low disorder.
Right.
So rubrine is actually this one here. You see, is one of the best performers when you consider disorder. So actually, if you could make rubrine more two-dimensional, that would be the greatest material ever.
And then there's a final question from Siri that I think is very interesting, is about whether the transient localization theory, I mean, you apply it to organic molecular crystals, and you show, applications to other materials as well. And there's a lot of, there's of course a large community of people working, for instance, on 2D materials, perovskite materials, or other materials that are interesting in that respect. Do you think that this transient localization theory could apply there as well?
Well, there is a PRL paper from last year from here from the institute, from Didier Mayou. They actually applied to perovskite materials and with some success. So the answer is yes.
Very interesting to hear. And I don't think we have additional questions, so it's probably a right time to stop here. I would like to thank you all the speakers, and also the participants for the active participation. I think it was a very nice session, and thank you very much. And so we'll meet soon for the poster session.